a distant frozen moon orbiting a colossal gas giant. For billions of years, it has remained a world encased in a thick shell of ice, silent and seemingly unchanging. But its ultimate destiny is not tied to the planet it serves, but to the slow, inevitable death of our own star. The end of our world could astonishingly signal the dawn of another, transforming this icy wasteland into a temporary water world, an oasis born from cosmic destruction. It's a future scenario for Jupiter's moon, Europa, a scenario grounded in the fundamental laws of astrophysics and brought to life through detailed scientific modeling.
To understand this dramatic future, we must first look at Europa as it exists today. It is the smallest of Jupiter's 4 Galilean moons, slightly smaller than Earth's moon, and its surface is one of the smoothest in the entire solar system. This eerie smoothness is a result of its global crust of water ice, scarred by a complex web of long cracks and reddish-brown streaks. For decades, scientists have been captivated by what might lie beneath this frozen shell. Evidence gathered from missions like the Voyager and Galileo spacecraft has strongly suggested the presence of a vast, saltwater ocean hidden deep below the ice. Data from the Galileo probe in particular revealed a weak magnetic field around Europa, one that changes as it moves through Jupiter's powerful magnetosphere. This variation strongly implies the existence of a conductive layer beneath the ice, with a global ocean of salty liquid water being the most likely candidate. The very surface of Europa, geologically young and featuring terrain that resembles floating icebergs on Earth, further supports the idea of a dynamic interior, where the icy crust shifts and breaks over a liquid layer. This hidden ocean could contain more than twice the amount of water found in all of Earth's oceans combined.
But in the freezing outer reaches of the solar system, how could such an ocean remain liquid? The answer lies in a relentless gravitational tug-of-war. Europa's orbit around Jupiter is not perfectly circular. It's a slight ellipse. This is due to the gravitational influence of the other large moons, Io and Ganymede. As Europa moves closer to and farther from Jupiter, the immense gravity of the gas giant stretches and flexes the small moon. Imagine repeatedly bending a metal wire. It generates heat. This same process, known as tidal heating, is happening within Europa on a massive scale. The constant internal friction generates enough warmth to keep the subterranean ocean from freezing solid, creating a potentially stable environment that has existed for billions of years. This hidden ocean, warmed from within and potentially interacting with a rocky sea floor through hydrothermal vents, has long been considered one of the most promising places in our solar system to search for extraterrestrial life. NASA's Europa Clipper mission, which launched in October of 2024 and is set to arrive in the Jovian system by April of 2030, is specifically designed to investigate Europa's habitability by confirming the ocean's existence, measuring the thickness of its ice shell, and scouting for any plumes of water vapor that might erupt into space.
This distant, intriguing world, however, is on a collision course with a dramatic change, one that originates from the very heart of our solar system. Our sun, the star that has nurtured life on Earth for billions of years, has a finite lifespan. In approximately 5 billion years, the hydrogen fuel in its core will begin to run out. With the outward push of nuclear fusion no longer balancing the inward pull of gravity, the core will start to collapse and heat up. This intense heat will cause the sun's outer layers to expand dramatically. The star will swell into a red giant, becoming hundreds of times larger and thousands of times brighter than it is today. Its expanding outer atmosphere will engulf the inner planets, consuming Mercury and Venus, and almost certainly our own planet, Earth. Even if Earth were to somehow escape being swallowed, the intense radiation would boil away its oceans and strip its atmosphere, rendering it a scorched, lifeless rock.
As the sun transforms, the so-called habitable zone, The region around a star where temperatures are just right for liquid water to exist on a surface will migrate outwards. The once temperate inner solar system will become an inferno, while the previously frozen outer regions will begin to warm significantly. And this is where Europa's story takes an extraordinary turn. According to models developed by astrophysicists, roughly 7 to 7.5 billion years from now, during the Sun's peak red giant phase, the Jupiter system will find itself in this newly positioned habitable zone. The distance from Jupiter to the surface of the bloated red giant sun could be comparable to the current distance between the Earth and our Sun today, around 150 million kilometers.
For Europa, this will trigger a profound and rapid transformation. Bathed in the intense light of the dying sun, its surface will begin to warm dramatically. Scientists predict that temperatures at its equator could rise to a balmy 42 degrees Celsius. The thick ice shell that has defined the moon for eons will start to thaw. But it won't just melt. In the thin atmosphere, the ice will undergo sublimation, turning directly from a solid into a gas. Water vapor will rise from the surface, creating clouds and a temporary humid atmosphere. This process will be accelerated by another factor. Europa is tidally locked with Jupiter, meaning the same hemisphere always faces the giant planet. This side will not only receive direct heat from the red giant sun, but also a significant amount of reflected light from Jupiter's own expanding and brightening cloud tops, creating an even warmer zone on the planet-facing side of the moon.
While this awakening sounds promising, it comes with limitations. Europa is smaller than our moon and possesses weak gravity. It wouldn't be able to hold onto a thick, dense atmosphere for a prolonged period. The water vapor would gradually escape into space. Therefore, a permanent, Earth-like surface ocean is unlikely. However, the models suggest a fascinating possibility. For a transient period, liquid water could become stable in certain areas. In low-lying regions such as impact craters or deep valleys, and in shaded areas away from the most direct sunlight, the atmospheric pressure might be just high enough to allow pools and lakes of liquid water to form. For the first time in its existence, Europa could have water on its surface, exposed to the light of a star.
This newfound temperate climate, however, will be fleeting. This golden age for Europa is predicted to last for only 200 to 500 million years. After this period, the red giant sun will exhaust its remaining fuel. Its outer layers will drift away into space, forming a beautiful planetary nebula, and all that will be left of our star will be its tiny, super-dense core, a white dwarf. This stellar remnant will be incredibly hot, but also very small, emitting far too little energy to keep the outer solar system warm. Europa's brief spring will end, and it will once again freeze over, returning to the silent, icy world it was before. From the perspective of life's evolution, a few 100 million years is a very short time. On Earth, it took nearly 1 billion years for the very first simple, single-celled organisms to appear, and several billion more for complex multicellular life to evolve. It's therefore highly improbable that complex life could arise and evolve on Europa's surface during this brief window of habitability. However, the more tantalizing question is what might already be there. If simple microbial life currently exists in Europa's subsurface ocean, this dramatic thawing event could bring it to the surface. For a few 100 million years, this hypothetical life would have access to a new energy source, sunlight, and a radically different environment. It would be a unique, albeit temporary, evolutionary opportunity. This entire scenario provides a fascinating template for what might be happening elsewhere in the universe. It shifts our perspective on where to look for life. Instead of focusing solely on planets around stable, sun-like stars, it suggests that the moons of gas giants orbiting aging red giants could host temporary habitable periods. This opens up a whole new category of potential worlds to investigate. For instance, astronomers have already found systems that bear a resemblance to this future state.
In the constellation Taurus, about 147 light-years away, a star named Epsilon Tauri, an orange giant, hosts a massive gas planet more than 7 times the mass of Jupiter. This planet orbits its star at a distance roughly 1.8 times that of Earth from the Sun. It is entirely plausible that a massive planet like this could have its own collection of icy moons. We don't yet have the technology to detect exomoons with certainty, but their existence is widely presumed. Perhaps on a moon orbiting that distant gas giant, a similar thaw is happening right now, a temporary paradise created by a dying star. The universe might be filled with these fleeting chances for life, brief windows of opportunity that open and close in the grand cosmic timescale, holding secrets that have been locked away under ice for billions of years.